Regardless of where you stand on the matter of data science sexiness, it's simply impossible to ignore the continuing importance of data as well as our ability to analyze, organize, and contextualize them. Data are changing how our businesses and societies function. They are being used to solve a ton of interesting problems and shaping the questions we can ask of the world around us. Hi, I'm James Lee, and this is Datacast. Join me for raw conversations with practitioners from the worlds of AI, machine learning, statistics, and data science. Hi everyone, welcome to a new episode with Datacast, and today I have the pleasure to speak with Karl Osipov. Karl is the Chief Technology Officer of Counterfactual.ai, a boutique machine learning consultancy that he co-founded with his friend from IBM. Previously, he held engineering and technical leadership roles at Google and IBM on programs and projects across both the United States and Europe in the areas of machine learning, computational natural language processing, cloud computing, and big data analytics. Karl is also an inventor with 6 patents at the USPTO and is an author of Serverless Machine Learning in Action, a book from Manning Publisher, currently available as an ebook subscription and expected in print in early 2021. So Karl, welcome to the show.
Thank you so much for hosting me, James. I'm looking forward to our conversation.
So I want to start out talking about your educational background. So I saw that you got your bachelor in computer science from the University of Rochester close to like 20 years ago. So yeah, can you describe your undergrad experience?
I'll be happy to. My undergraduate experience in computer science was really formative for my career and formative in terms of motivating me to work in the areas of machine learning and data science. I spent 3 years getting my bachelor's degree in computer science at the University of Rochester. I also managed to get a minor in economics while I was there. So it was a very busy time, but it was also a rewarding time. I was fortunate to join the program with some experience in programming. So I started programming very early. As a kid, my father actually got me started programming on those IBM mainframes, the OS 360 machines. So I actually had a chance to play around with punch cards. So I have programmed for quite some time before I joined the computer science degree at University of Rochester. So that helped. But what was entirely new to me during that program was the opportunity to do undergraduate research and meet some fantastic professors. So some professors that come to mind were Dana Ballard. He was one of the participants in what was known as the connectionist movement that produced such key figures as Jeff Hinton, Young Kuhn, and others in machine learning. So obviously Dana Ballard doesn't have the same name recognition, but it was an awesome opportunity to form a relationship and learn from somebody who created one of the most formative books for me in the machine learning space. The book title is Natural Computation, and also to understand how research is done at a small research university like University of Rochester. Probably another professor that was really influential was Rendell Nelson. So I took computer vision classes from Rendell Nelson and learned a lot. So unfortunately, I had to leave the university early in 3 years. I am an immigrant. I came to the United States when I was 14, and I was put in a situation where I had to financially support my family. So unfortunately, I had to graduate earlier than I would have liked. So I would have stayed at the university for more than 3 years if I could, but had to go out and find a job.
And so my understanding is that, in one of our early conversation before the show, you said that you implement your first fully connected to Turing-based artificial neural networks using C programming language back in 2000, when using neural networks wasn't nearly as cool as it is today. So would you mind sharing that anecdote?
Absolutely. So I mentioned Randall Nelson, who taught computer vision at University of Rochester, and I took a class. This was a graduate level computer vision class, where one of the projects was to process a digital image of fruit. So think of a digital image of fruit that contained apples and oranges. And the task was to actually count the number of apples and oranges. So at that time, no one really was using neural networks for this type of a problem. When I say no one, I mean no one in the class. So after chatting with some of the fellow students, I decided, hey, why not use this as an opportunity to try out neural networks? So this was a fun class. Obviously, back then, I didn't even know about convolutional neural networks. The algorithms like YOLO weren't even on the radar. So this was a very, very naive approach where I tried to recognize fruits, apples and oranges using a two hidden layer fully connected neural net. Actually implemented in C, so I had to use pointers. I had to manage memory manually. I remember I had to work out the chain rule for the sigmoid activations. So the reason I actually used sigmoid activations back then is that finding the derivative analytically was easier than with other activation functions. So ultimately that failed. So obviously I couldn't count up the number of apples and oranges. Didn't work well at all. But I think I learned a lot, and actually I built a little neural network library that I later reused in some of my other research projects. Mm-hmm. So something good came out of it.
Convolutional neural network doesn't even exist until like 1998, right? So there was literally like the earliest day of this field. I think Jan LeCun invented it in 1998. So yeah, it's great to hear that you already have some sort of exposure to it, even in the naive way back then.
Well, from my standpoint, I think actually no one in the class succeeded in solving the problem. So I think I was vindicated in that approach. But just to give you a sense of how much the field has advanced in 20 years, back then, none of the graduate students could solve the problem. And in just 20 years later, you can have an undergraduate download a machine learning framework and a library off the internet and easily solve that problem in less than a week.
I see. Yeah, you talk about leaving UBR early to start your career, and you work as a software engineer at IBM right after college. Can you discuss a couple of the main projects that you contributed to during your first 6 years as an individual contributor at IBM?
Absolutely. I think the first job that I had out of college at IBM was really formative in terms of helping me understand how to build large-scale distributed systems. So I mentioned this experience in doing machine learning in the small at university, these little research projects, experiments. The first job that I joined at IBM was actually on a project where IBM was building out a cutting-edge semiconductor manufacturing plant. So in the industry, we call these fabs. This is a place where companies actually manufacture computer chips. So back in 2001, I joined as a software engineer, and I was responsible for C++ and Java software that connected the various pieces of equipment on the floor of a fab to the overall system that controlled the manufacturing. So this meant that I had to really build out skills for implementing high performance and high reliability Java code. And also this taught me a lot about working on extremely large scale projects. So when I say extremely large scale, let me explain what that means. The fab itself was a massive investment by IBM. It was over $2 billion of investment to build out that fab. It was a massive project just in terms of the floor space. So imagine football fields, like 5 football fields stacked one next to each other to give you a sense of the size of the fab as the floor space. And the project itself was successful. Of course, I played a small part in it. It was my software engineering contributions, but the fab itself at the time was producing computer chips for some of the top consoles. For example, for the Xbox, Nintendo, and PlayStation.
Mhm.
So there were a lot of interesting challenges. And what that first experience out of college taught me was to really how to approach development of distributed systems in a way that these systems are resilient to change. So these are really software engineering concerns. And also how to build out systems that can scale up. So the neural networks that I was working on at university did not scale up at all. But all of the systems that we had to build at Building 323, which was the name of this location for the semiconductor fab for IBM, all the systems had to scale up to hundreds of these pieces of equipment that would actually process wafers, create computer chips on the wafers, and do various kinds of testing. So really one of a kind of experience with software engineering. I spent about 2 years working at that fab. And then I got that data and machine learning itch again. So I wanted to shift into something more research oriented than working at the manufacturing facility of IBM, working on pure software. So I was also fortunate to change jobs while at IBM. So I went from the systems organization of IBM to another organization known as IBM TJ Watson Research Center. And I spent about 2 years there as well, also working as a software engineer on a very interesting project where IBM was building out what were at the time first of a kind voice recognition systems and dialogue management systems. So there I worked on machine learning for natural language processing, doing things like text classification, entity recognition, and really putting these machine learning subsystems together into an end-to-end system that would interact with customers of financial institutions and help them manage their 401k accounts.
And I believe like IBM Watson, during that time was probably one of the first industry application of AI machine learning, right? Participating in Jeopardy and was actually kind of get the interest of the public to this field, at least in a commercial level, I believe.
So at that time, IBM was one of the leaders in topics like machine translation. So definitely one of the areas of natural language processing. Unfortunately, I did not have the opportunity to work on Watson that played the Jeopardy game. That happened a little bit after my time there. But at that time, this was a cutting edge research lab. Definitely a lot of exciting work in machine learning. And I had some once in a lifetime of kinds of opportunities. Like, for example, I had a chance to have lunch with Benoit Mandelbrot, who was there. And obviously he is father of fractals and fractal mathematics.
Yeah, and so I want to dig deeper on sort of the machine learning system on NLP that you just mentioned. It was called Conversation Interaction Manager, and as you already mentioned, it's a dialogue management system for conversational mixed initiative natural language application. What is some of the motivation behind this project? What are some engineering challenges that come up during its development? And what are the business outcomes from its adoption?
Sure. So let me try to address these one by one. In terms of the motivation behind the project was at the time, so that was nearly 20 years ago. So at that time, the customer for the project was T. Rowe Price, one of the top companies in the space of retirement plans. And the goal of the project was to develop what was known at the lab as a first of a kind, or FOAK for short, a first of a kind project, demonstrating how to build a system that acts as a telephony application. So in other words, you can actually call the system over the phone and talk to the system almost as if you would talk to a human representative. So using natural language interactions. So the motivation for T. Rowe Price obviously was to understand what they could do in terms of transitioning some of the 401k support issues to this kind of a telephony system and understanding the capabilities of the voice recognition, dialogue management, natural language processing components that were available at the time. So all of that, of course, is pre-deep learning. So think 2003, 2004 timeframe. So the motivation, obviously, for the customer's T. Rowe Prize that was featured in a Wall Street Journal article, and then some of the other financial industry customers, was to really understand how they could build a business case around this technology. And if we shift gears and start talking about the engineering challenges, there were plenty. So in the areas where I worked on, which were primarily on integration between machine learning subsystems and dialogue management, if I think about the engineering challenges that kept me up at night, the main ones actually would be something that we would describe today as DevOps. It was exceptionally difficult for us to automate the process of creating new releases of software and then delivering those releases of software to the customer. So when I say exceptionally difficult, I really mean that we had to compile the software that had C code, had Java code, save it as a tarball, and then actually send it over to the customer, which was the IT organization at T. Rowe Price and later was other financial companies. So if you think about the modern approaches for building and releasing software, where you can generate hundreds of releases a day, where you have completely automated continuous integration, continuous delivery pipeline, this is night and day. So from my standpoint, this was probably one of the single biggest engineering challenges that was an impediment to us delivering new features quickly to the customer. So this is probably the biggest engineering challenges, but the listeners are probably more interested in the machine learning challenges. And if I think about the machine learning challenges, honestly, they haven't changed that much. So when I think about the engineering challenges back then for cleaning up data, for example, we worked with massive amounts of text. So sample recordings of people calling into this voice telephony system and saying things like, I want to know the balance of my 401k account, or I want to transfer $10,000 from Asia Pacific fund to the US stock index fund. So we had massive number of recordings of text like that, and we had that text in text files. So back then, to work on data quality, we would write Emacs macros to handle text. And when I look at modern techniques for natural language processing, I think the data quality tools have not improved substantially since then. We moved to a nicer user interface, but I think the data quality productivity is still lacking. So if I were to describe a single top machine learning challenge, it's still data quality. So actually in my book, in Serverless Machine Learning in Action, I dedicate almost an entire chapter to data quality. So there I talk about the vacuum framework that anyone working with data can adopt to help them organize the approach to data quality. So even though it used to be a challenge and is still a challenge, I think we've made some progress in understanding how to at least approach this challenge and be more productive when dealing with data quality. Mm-hmm. And then I think the last part of your question had to do with the business outcomes for the adoption. And there I have to probably disappoint you, because the business outcome was not nearly as good as what it could have been. So I think at that time, the project really was structured as a research project, trying to understand what was possible, as opposed to try to build a business or a profitable business with practical technologies. So again, remember, this was way before the deep learning days. This is voice recognition before applications of deep neural networks. So the voice recognition component wasn't great. It wasn't great with mobile devices that were just getting popular in the mid-2000 timeframe. So overall, the project as a business failed, but I think it ended up generating a lot of insights, both for IBM and for myself, in terms of where the industry should go to become more productive at delivering this kind of machine learning projects.
Yeah, thanks for sharing your takeaway, right? And especially those key points on the challenges associated with DevOps engineering and data quality for the application. So I believe the second production machine learning system that you work on is called Smarter Campus, which is a project that enables staffing recommendations based on social networking, optimization, and text analytics. And so what is the idea behind it? And what are some of the different components making up the system?
So when I talk about the motivations, the ideas behind Smarter Campus and the components, let me start with the high-level idea. Smarter Campus was really one of the projects where I had my first serious leadership role while at IBM. So I was the software architect for the system. If you think about the motivational idea behind the project, you have to think about the IBM software group that was led by Steve Mills at the time. And IBM Software Group was struggling with this idea of delivering cross-business unit software. So within IBM, we had different business units. There was, for example, a WebSphere business unit that focused on integration middleware. There was a business unit that focused on collaborative tools like Lotus, others as well. However, what was missing was an organization that would help build out solutions that would tap into software across these different business units. So at that time, IBM was looking into this idea of Smarter Campus as a way to create this cross-business unit software for a particular industry. And of course, in case of Smarter Campus, the industry was higher education and as well as corporate research. And the idea for Smarter Campus specifically was to take some of the IBM collaborative software. In particular case, there was a product known as IBM Connections, Lotus Connections, that was providing a social network, on-premises social network for company employees or for faculty and students at a university. There was another component that was providing text analytics. So for example, there was a InfoSphere tool that would handle recognition of named entities, for example, names of universities or names of research paper publications in natural language text. And the project was to pull these components together into the tool that would help build out a profile, a skills-based profile of a faculty member, of a researcher, and help these faculty members build out teams that would help faculty be more effective in going after research grants. So that's the high level idea, and let me unpack that into components to explain how this worked. So if you think about individual researchers typically have websites where they put together their research publications, hyperlinks to research publications. They put together links to the courses that they teach, content of that sort. And the text analytics component actually would crawl the web pages of researchers. So for example, we started a pilot project with University of Rhode Island, where we parsed out the research publications for researchers working in the Department of Biology and try to understand their research. And as part of this text analytics parsing, we would basically parse out the natural language text of research publications to try to detect keywords that would best represent profile of the researcher. So in this case, I'm probably getting too much into the weeds, but the idea was to capture some of the most popular keywords and n-grams from researcher publications, and then compare those n-grams using Kalbeck-Liebert divergence, scale divergence, to the research publications of other professors in the same department or working on publications that get published in similar kinds of journals. So the idea was to find the most common research publications that would be different from the most common keywords and most common n-grams for the other professors working in a similar kind of a field. So sort of trying to focus on unique identifiers for professors as opposed to something else. And we built out this text analytic systems, text analytic subsystems, this crawling and natural language text pipeline. That worked quite well. It worked so well that at University of Rhode Island, one of the administrators for the research department took out these printouts of the top keywords and created a word cloud out of them. So if you've ever seen a word cloud diagram, he almost printed out a portrait of a different researcher together with their corresponding word cloud. And that helped them create sort of a visual way of understanding what kind of work a particular researcher is doing. it was a good way for the research administrators to understand what their professors or what their researchers were working on without having to read the research papers themselves. So that's the text analytics part, and the social networking part was really about helping put together these top keywords, top n-grams that we identified automatically, and present them on the social networking page of each individual researcher. So I mentioned that we crawled these raw web pages that researchers put together, but we used the results of these text scrolls, these n-grams and keywords, as almost like a widget. If you imagine a social networking page, like a Facebook page for a researcher, we populated automatically the social networking pages in the IBM Connections product with different researchers, and helped researchers search for other professors, other faculty members in different departments that are doing adjacent work, that are basically working on similar kind of keywords, similar kind of n-grams as they are. And the idea there was to help a faculty member to go after a research grant and try to find experts on the topics mentioned in the research grants, where the faculty members weren't necessarily experts themselves. So finding collaborators, really.
Yeah, that's awesome. That's great to hear that your project you're working on has a great impact towards university system, and make it easier for professors to get connected to the grants that you already mentioned. Back to your work at IBM, you just mentioned that this work, Sparta Campus that you work on, was happened during your leadership role at IBM. Right. So my understanding is that after working as an individual contributor for 6 years, in the next 10 years or so, you move on to various leadership roles at IBM, such as lead software architect, business development executive, developer advocate, and executive IT architect. And in particular, you led some of the projects and programs across the US and Europe in machine learning, NLP, cloud computing, big data, and service-oriented architecture. So, would you mind unpacking the evolution of your career at IBM, including the scale of the company that reached over 1 million registered users?
I'd be happy to. So IBM, at the time that I was there, and I think it's still the case today, has a very structured career progression for someone who is interested in moving along the technical leadership career path. And that explains some of the different opportunities that I've had. So I had an opportunity to shift into more of a business role. I actually spent 2 years as an expat in Prague, Czech Republic, helping IBM grow the cloud computing business there. And the specific project that you mentioned, I was recognized with an award and as a top contributor to a project known as IBM Bluemix that later got rolled into the overall IBM Cloud brand name. And specifically, my role on the IBM Bluemix project was initially as a developer advocate. So for the listeners who have not seen developer advocates in the past, it used to be in the pre-COVID days that companies would participate in trade shows. And at these trade shows, you would have an opportunity as a developer advocate to interact with attendees of trade shows, talk to them about your product, in this case, this IBM Bluemix product, and also help run demonstrations, sessions, essentially spread the word about the product and help generate demand for the product. So that was more of a marketing-oriented experience. And when I talk about Bluemix, if you're wondering what is Bluemix, Bluemix was the brand name that IBM used for a platform as a service offering. So if you think about technologies that help you take your existing code and deploy it as a service into the cloud, that's roughly what IBM Bluemix offered. And then over time, Bluemix expanded to also add other capabilities. So for example, I spent a lot of time helping to flesh out IBM Bluemix capabilities around big data analytics, using some of the early Watson technologies for natural language analytics, and also using some technologies like Apache Spark on top of Bluemix in order to help customers build and run the Apache Spark applications in the Bluemix environment. So one of the examples of what I worked on there as a demonstration for customers was to help customers, for example, build a Spark application that would process data, massive amounts of data from sensors. So imagine somebody using like a Fitbit sensor on their wrist, and then sharing sensor data that captures information like heart rate, and then also some sensor data that captures location of the individuals, and use that to figure out if the individuals were walking, if they were running, or if they were using a bike or a car. So building those kinds of data processing systems and ML systems to solve classification problems, basically. This multivariate classification problem for deciding, based on raw sensor data, what kind of motion is the user performing, right, for these 4 different classes. So it was an exciting project, and in particular, you asked me about how do you scale to 1 million registered users. So initially, when we launched Bluemix, and that was 2015 timeframe, 2014, 2015 timeframe, it was just an IBM internal project. So internally at IBM, we had users that would deploy their applications, but Bluemix was not open to the outside world. And I guess if you want to know how do you scale to 1 million users, the simple answer is that you scale 1 user at a time. For the audience, you're wondering about machine learning approaches to that scale. The reality is that at those initial levels, much of the work that you need to do to scale up your product is in going out and talking to customers. Mm-hmm. So one of the things that I learned in these less software-oriented roles as a developer advocate, and then also from the business development standpoint, is the importance of talking to customers, the importance of understanding your customers. And really, if you want to take something that has no traction at all in the marketplace, as Bluemix had at the time, it's extremely important to have face-to-face conversations with people and try to understand who are the people who find your product interesting. In other words, try to find the individuals who will resonate with your message about the product. And of course, for us, it was developers. So we spent a lot of time as the developer advocacy team going out to trade shows in the Bay Area, in New York, other trade shows worldwide, talking to customers and spreading the word about Bluemix.
I see. Yeah, thanks for sharing that anecdote and really emphasizing on the importance of doing things that don't scale, like talking to customer, to find the product market fit for this new software that you have developed. And yeah, also the importance of like being a developer advocate, understanding your audience. It's really, really important for whatever kind of software initiatives that you or your company is working on. So I believe during the late 2000s, you also pursue a master's degree in computer science from the University of Florida. So can you talk about this decision to, get a graduate degree?
I mentioned a little bit early in the interview that I left University of Rochester with a little bit of a bittersweet feeling, right? So on one hand, I got my degree. I got my major in computer science, minor in economics, but I felt like I wanted to stay there, but I really had to go for financial reasons. I had to go and find a job. I was very fortunate because in late 2000s, I had a wonderful vice president at IBM. Her name is Catherine Fraze, and she was supportive of me going back and getting my master's degree. So for a few years, while I was a software engineer at IBM, I actually also was doing graduate school part-time to complete a master's in computer science. So at that time, I also focused on my machine learning skills, but I focused on them from a different point of view. I think at University of Rochester, I got more of an applied perspective on machine learning, while at University of Florida, I had an opportunity to do a deeper dive into the theory. So for example, Christopher Bishop's book on machine learning was quite popular at the time. And one of my machine learning classes was about learning the theory, learning some of the foundational Bayesian ideas behind machine learning, some of the foundational ideas behind probability. And understanding machine learning in depth. So really, I value my experience at University of Florida from the standpoint of having an opportunity to work in the industry as a software engineer, but at the same time deepen my understanding of machine learning from the theoretical standpoint.
Yeah, perfect. At University of Florida, you wrote a research paper called Amaga Cloud, Social Networking Adaptation for Human and Computational Agent Team Formation, which is later presented at the Automated Software Engineering 2012 conference. And I believe the paper focused on the relationship between network adaptation for candidate group participation and the performance of problem-solving groups. So yeah, can you unpack the background and the core contributions in this paper?
Absolutely. So at the time, one of the reasons why I co-authored that paper was because I was on the fence about pursuing the PhD program at University of Central Florida. So at that time, I was thinking about where to take my learnings about machine learning next, and whether I want to do an academic study of machine learning, try to put together a thesis. Ultimately, I decided against doing a PhD program, but as part of my exploration of that idea, I ended up with this paper. Just to set context for the paper, if you've done machine learning for a while, and here I speak to the audience who have really delved deep into machine learning, ultimately you realize that the limits of machine learning as it exists today is about the loss functions that you're using. And then the question comes up, okay, so if you have these loss functions, you have this field of optimization theory, what can you do to try to make more sophisticated machine learning algorithms? And even back while I was working with Dana Ballard in the undergraduate research programs, it was clear that you should be thinking about the ideas from game theory. In Dana Ballard's book, Natural Computation, one of the concluding sections in that book is about game theory. And the idea is that if you cannot really create loss functions yourself for your problem, maybe you should use these ideas from game theory like Nash equilibrium to help create environments where you can train competitive machine learning models and design machine learning models using game theoretic approaches, which is easier for people to reason about than try to engineer highly complex loss functions. So obviously there's a famous success story that came out of this idea, which is GANs. Personally, I had nothing to do with GANs. I really admire the work on GANs and the way that GANs connect game theory to machine learning. And I think it's the most famous example of achieving practical results of connecting these two fields. So I think more can be done in that space. The paper that you cited is my attempt to try to connect game theory to machine learning. That was a failed attempt, right? In the scope of things, obviously, I measure my success there by comparison to GANs, and from that standpoint, obviously, that paper was a complete failure. But I did learn a lot from it. So the key contribution of the paper was to look at this idea of how can you create teams of different agents. So again, if you think back to the idea behind machine learning, if it's very difficult to craft complex loss functions for machine learning, what if you can think about crafting collaborative machine learning models in a game theoretic setting and try to encourage these machine learning models to collaborate, to have complementary skills? So the key contribution of the research paper is a simulation-based study that looks at the possibilities of these agents. Think of these agents as independent machine learning models that are highly skilled at some small problem. How can you understand, how can you simulate these machine learning models, these agents, coming together into teams that have complementary capabilities so that you can solve higher order problems? If you're interested, as a listener of this podcast, I really encourage you to just download the PDF of that paper and check it out.
Yeah, actually, game theory, when you mentioned, you try to attempt to kind of bridge the gap between game theory and machine learning. I think one of the things that also come to mind is the application of Shapley values for machine learning interpretability. I think that is something that's also quite hot these days. Essentially the idea of like measuring different contribution of different features in the final prediction, and then try to figure out which features had highest importance. So yeah, it seems like it kind of follows along the similar framework that you mentioned in terms of team dynamics and what contributes to the eventual loss function of a model, right?
So I think the distinction is, if you think about machine learning interpretability, it takes a retrospective point of view on machine learning. So it looks at existing machine learning models and helps you understand how they work. The distinction with the paper that I described is that it takes more of a design-oriented point of view for machine learning models, a prospective point of view. So in other words, if you have a goal for a machine learning model, how do you design it ahead of time rather than trying to figure out how does an existing model work?
Diving further into your publication, I found another patent called Learning Ontologies for Machine Learning. So can you talk about the challenges of mapping ontologies in computer system and how this work addressed those issues?
The specific patent on mapping ontologies came out of the work that I was doing together with a research team at IBM. So at the time when I was working on this ontology mapping problem, IBM was investing heavily into building out what are known as industry-specific solutions. And one of the technologies that exists in fairly mature, and I say mature, I mean mature from the information technology standpoint industries, is this idea of a data warehouse and the data warehouse maturity. So imagine you are a retail bank and you need to be able to capture almost every aspect of your business in a data warehouse. So you want to keep track of the customers, because the banks are highly regulated customers. They're highly regulated industry players. They have to comply with government requirements known as know your customer rule. So they're collecting almost like a 360 point of view on their customers. Banks have to collect, obviously, financial information about accounts. They have to keep track of the different offerings, products that they collect, and so forth. And one of the projects that I worked on was the research team at IBM was helping banks solve the problem of what happens when one bank acquires another bank. And in the process or following the acquisition, they need to be able to reconcile their data warehouses. So if you imagine these data warehouses developing organically, how do you actually figure out the process for mapping different tables in these data warehouses to each other? So imagine massive data warehouses that have up to thousands, single-digit thousands of these tables in a data warehouse. And the names for these tables are distinct between two different banks that are going for the merger or going for the acquisition. From the standpoint of the machine learning problem there, the idea behind the patent is to look at some of the common problems that happen when you try to reconcile these data warehouse ontologies. So the approach that the team initially used to reconcile was to actually look at the documentation for these data warehouses and try to use the keywords describing the tables in the data warehouse to do the mapping. It's almost like this matching problem. Think of it as a matrix, where along the rows of that matrix you have the documentation keywords from one bank for different tables. Along the columns you have the keywords from the documentation for the tables from another bank, and you're trying to find out the counts of where the keywords match. So very, very naive approach to try to find the matching entities between these two different data warehouse tables. So the example would be, let's say if you have a table for something like customer information in one bank, and then maybe a customer record table in another bank, your hope is that by looking at the documentation, the scanned documentation that exists for these tables, you would be able to see mentions of the words customer, information, record, maybe mentions of something like description of a customer, mention of a customer, address, and so forth. And just by looking at the counts of these keywords, you would be able to get a pretty good guess that the tables match, that both the customer information and the customer record table actually store roughly the same thing. And then you can extend this idea and also do counts on the individual column names within the tables and so forth. So unfortunately, this approach, while it sort of works, it doesn't work very well, and it fails in the situation where you have these table names that are very close to each other, but are very general. So if in the example that I gave, the customer information and customer record table names, obviously the word customer comes up quite a bit. And the keywords also are commonly used, for example, with the other tables that might include something like address information or phone information or phone record. And the issue is that the documentation becomes very ambiguous very quickly. So for example, in the address information table, you might also have keywords saying, hey, this is the customer address information. So the systems get confused very, very quickly. And the patent is about helping to improve on this problem. The patent is about using natural language processing to try to recognize these ambiguous entities ahead of time. So in the patent, I co-authored with this research team. It's about identifying these potentially ambiguous table names ahead of time. For example, the table name like a customer info and a customer record, splitting up those table names into the fact that it talks about the customer and then talks about information, picking up the more salient part or the most salient keyword like the customer instead of the information keyword, and using those more salient keywords to actually do the matching, so that if you work with table names like customer info and customer record, what you focus on are specifically the customer aspect of the table, not the more general keywords like information or record.
Awesome. Yeah, thanks for sharing the details about that patent. Again, back to your work at IBM, I found your blog, a 4-part blog series, dated back in 2016 that, essentially discussed serverless computing. And so, could you mind quickly summarizing some of the things that you cover in this blog series?
Absolutely. At that time, serverless was just becoming popular in the information technology industry, and a particular flavor of serverless that was popular at the time was known as functions as a service. So one of the most well-known examples were AWS Lambda, which helped developers to write a function, think a Python function, and then deploy it in a cloud-based environment, and then basically let that function act as a web service on the internet. Back then, in this blog post, I was describing a complementary technology in the marketplace known as Apache OpenWhisk. So Apache OpenWhisk is powered by Docker, a container technology. And the idea behind OpenWhisk is to provide support for virtually any programming language, not just for Python or Go, not just to a limited set. So with Docker, it's actually possible to deploy a specific programming language runtime. So let's say you are an R developer and you'd like to deploy an R function as a service into the cloud. So with Docker, you can actually set up a Docker container that allows you to do that and deploy it out into OpenWhisk infrastructure and have your R function act as a service. So within that blog post series, I talk about the value of the serverless approach, and specifically I talk about the fact that if you're using serverless as a machine learning practitioner or as a developer, you can really make yourself more productive by focusing on writing code, focusing on writing these functions, as opposed to focusing on the operations aspect. So when you think about the potential for these containers, for these functions, it becomes obvious very quickly that it's possible to scale up this approach to potentially millions of these function invocations, because you simply have a function running as a service somewhere on the internet. So you can potentially scale your code very, very quickly. And it used to be with the approaches before serverless that you had to worry about the operations. So in other words, you have to ask yourself, okay, if I put a web service out there into the cloud, if I use infrastructure as a service-based approach where you put your code into virtual servers, or if you use a platform as a service-based approach where you put your code into this application running in the cloud, the operational concerns begin to overwhelm a practitioner very, very quickly. So if, for example, if you're a machine learning developer and you build a very small machine learning model, let's say you build a logistic regression model that's doing a prediction of estimated time of arrival for food delivery. The model itself can be fairly small, fairly simple, definitely something you can package into a few megabytes of code as a Python function. But the problem is, even though it's possible to put that model out on the web very, very easily, you have to ask yourself, what does it mean for this model to be running in production over, let's say, a year or 2-year time frame, right? If you have a valuable model there. And that's where these operational overheads quickly become overwhelming. So for example, if you are running this ETA model in production as infrastructure as a service, you have to ask yourself, do I have the right number of these virtual servers that you have to manage? How do you elastically scale those virtual servers running your model? What happens if a security problem is discovered in the operating system of those virtual servers? How do you go in and manage the updates to the operating systems? So that's infrastructure as a service. If you're working with platform as a service, the concern is your model might be running as an application in the cloud, but then you have to ask yourself, okay, it's running as an application in some middleware. So for example, if you're deploying your model in Python, it might be running as a Python Flask application, web app. And then you have to go in and ask yourself, it's end of life of Python 2 deployment. How do I transition that application from Python 2 to Python 3? So really the value of the serverless approach is that you can really focus on your code and outsource all these operational concerns, everything from managing middleware, the runtimes, to managing the operating systems and security updates to the cloud provider. So in this 4-part block series, I explain the value of the serverless approach in terms of reducing the operational overhead, and then I provide some illustrations for common patterns of using serverless. So patterns that involve, for example, building a simple application for sending out text messages based on these functions as a service. There's some examples for doing data processing using patterns that are similar but different to extract, transform, load pipelines, and a few other patterns for serverless as well.
Awesome, and definitely recommend anyone interested to read that blog series, especially in the final post of that series, you discuss the major differences between, like you already mentioned, serverless and platform as a service and ETL architecture, as well as some of the architectural patterns like enrich, comment, and persist, which I think have a very nice summary of those benefits that serverless might bring upon towards your ML system. For the audience who are not familiar with, let's say, Docker or any other container-based technologies for serverless computing, what resources could you recommend following?
If you're a data scientist or a machine learning practitioner, and a part of your job is to actually put your machine learning models in production, I would say you need to spend some time learning Docker. If you don't know Docker today, I would actually recommend my book, Serverless Machine Learning in Action, as a place to get started, because it will not only teach you about Docker, it'll teach you about how to use Docker and container technologies in serverless setting to be a more productive practitioner. And when I say more productive, I mean you will be able not only build machine learning models, you'll be able to scale them up in a deployed environment. So definitely check out my book if you want to have an experience with a project of applying Docker. But if you are purely interested in using Docker or learning about the APIs for Docker, Docker.com actually has a great lab environment where you can go in and start experimenting with the Docker command line interface. So if you have 15 minutes and you want to quickly play with Docker, check out one of these labs on Docker.com.
Actually, I attended the virtual Docker Conf a couple of weeks ago, which is really cool. I think it's totally free, and then there's a lot of interesting session from the Docker community and different companies that are using Docker and Kubernetes, things like that in the company. And so yeah, definitely, I believe this community has been existing for like very very long time, way longer than the machine community. So it's quite established at this point. I can certainly affirm that there's a lot of great resources out there to start out with. Yeah, so we will talk about serverless computing later in the episode, but before that, I believe in mid 2017 you transitioned into a new role as a program manager at Google and have managed the company's efforts to democratize machine learning. So what are some of the primary responsibilities and initiatives that you provided at Google?
So specifically at Google, I had a unique opportunity. I actually came on board very early on one of the initiatives known as an Advanced Solutions Lab. So an Advanced Solutions Lab is an offering from Google Cloud Professional Services where Google Cloud customers can actually come on site. And again, remember, this is pre-COVID-19 days. So a team of machine learning practitioners, data scientists would come on site to Google. At the time when I was joined, it was just on site to the Google Sunnyvale location. And they would spend almost a month working directly with Google engineers and learning from them on how to build machine learning systems that they can take back to their employer and build a business use case around these prototypes of machine learning systems they built together with Google engineers. So when I came on board to Google Cloud, I actually had an opportunity to be there very early. I actually was a manager, people manager for one of the first engineers who taught machine learning practitioners through this Advanced Solutions Lab ASL program. Of course, while I was there, the program scaled up quite a lot. And one of my roles was in the enablement. So if you think about this program, the way that it's structured is that it's partially about teaching and partially about deployment. So when I say about teaching, as part of this ASL program, a customer actually spends their morning and part of the afternoon attending lectures from Google engineers, and then they spend the evenings building out a prototype machine learning system that they can later take to their employer for a build out of a business case. So the learning materials are a key component of this program. So much of what I've done with Google was in helping to flesh out a lot of this learning material, focusing on machine learning, data engineering, and data analytics, and spent quite a bit of time talking to developers at boot camps, talking to developers at various trade shows about the kind of learnings that they can get from Google Cloud, not just from the Advanced Solutions Lab, but from the other Google Cloud offerings as well. For example, from the certification program that use the same learning content, from the training program and others. So, for example, one of the things that I've done while I was there in terms of helping to democratize artificial intelligence for the world is that I presented at the O'Reilly Strata conference on some of these techniques for using serverless machine learning with TensorFlow. So that was really where I think matured the ideas around using serverless and machine learning together and presented those ideas to the world. There was a lot of interest in using serverless machine learning. And I think that prepared me to write the book. So in the book that I currently am working on with Manning Publishers, it's actually using PyTorch instead of TensorFlow. Because of my customers, I actually transitioned from using Google Cloud to using AWS. Most of my customers are actually asking for PyTorch and AWS solutions. So I think even though I started to help democratize artificial intelligence while at Google, to some extent, I'm still helping to do that. And right now I'm doing that for my book.
And talking about, you mentioned about teaching these concepts, to practitioners. So you led the 2017 Google Go Datacast in Amsterdam that taught participants ML and TensorFlow concepts along with hands-on skill in developing, evaluating, and productionizing ML models. So, I'm just curious, what was your experience as a bootcamp instructor?
That was a lot of fun. So I mentioned as part of my role at Google, I worked heavily on fleshing out the teaching materials for the for Advanced Solutions Lab and other Google Cloud programs. And these boot camps that I held even before Strata, so the one that you mentioned was in Amsterdam, these boot camps were an opportunity to beta test a few things. They were an opportunity to beta test what I call my 3 C's of responsibilities that I had at Google. So the C's stand for code, content, and collateral. So obviously, if you're running one of these hands-on boot camps, you have to provide your bootcamp participants with code. So I'm talking about really the code that they can use to help jumpstart their machine learning efforts. So instead of building out machine learning code that uses data sets in Google Cloud from scratch, they already have some pre-written code that they can reuse, almost like a Lego bricks, to pull the machine learning solution together. So that was the code component that I had the chance to beta test at this bootcamp. The next piece is the content. So when I talk about the content, think about all the documentation, the slides that go into running one of these boot camps, everything from explanation of TensorFlow, explanation of Google Cloud, all the way down to the slides that help students get on board into the bootcamp and get started with the code. And the last thing is collateral. So as a program manager, right, I was responsible for making sure that these bootcamps are successful. And what makes a bootcamp successful is not just the experience while you're at the bootcamp. It's also the ability to generate demand for the bootcamp so that the people are excited, and then you have the right people joining the bootcamp in the first place. So when I talk about the collateral for one of these bootcamps, this is more about demand generation collateral. So think about marketing brochures that you can hand out at trade shows. Think about email content that you can send out to interested participants, those kinds of things. So I think all these 3 C's, code, content, and collateral, is what it takes to make one of these boot camps, one of these learning experiences, and even programs like ASL successful.
I also found another excellent talk at the Google's 2018 Data Cloud Next event, in which you went over Google BigQuery's support for semi-structured data analysis. So, why do semi-structured data matter, and how does BigQuery come into play?
Semi-structured data is extremely important, and from my point of view, obviously I did that talk, so I'm biased. I think it's underused. So let me take a step back and explain what I mean exactly by semi-structured data. Obviously, the listeners are familiar with structured data, tabular data organized into rows and columns, and unstructured data. So when I say unstructured data, think data that is in a formats like audio, video, photographs, natural language documents, etc. However, there is this middle ground of semi-structured data where some of the values are allowed to be almost in a structured format, but not entirely. So let me give a specific example. If you think about data in a JSON format, most of that data is effectively structured. You can think about key value pairs in JSON data as column names and values in individual rows. But in formats like JSON, right, JavaScript object notation, it's also possible to have data that's organized into arrays, for instance, or data that's organized in a very nested format like dictionaries. So this kind of data in the JSON format is actually extremely popular for software engineers, for developers. In fact, if you are a machine learning practitioner or if you're a data scientist, you may not know this, but when you're using web applications, when you're using a web page, you probably don't realize that a lot of the interaction that happens between your browser and the web server of the web application happens using this JavaScript object notation, this JSON format that's highly semi-structured. It has a lot of these array values. It has highly nested dictionary values behind the scenes. So if you think about the growth of popularity of application programming interfaces, APIs, they're growing exponentially. In fact, while the growth of internet use by human beings is sort of flattening out, right? We passed the peak of that growth. The growth of APIs or interactions via APIs on the internet is still continuing. And that has to do with more and more devices becoming available on the internet. It has to do with the fact that more and more machine-to-machine IoT, Internet of Things kind of applications is still happening. So these APIs and the data that traverses in between the APIs is extremely important. So in the talk that you mentioned, I describe how you can use a serverless data warehouse such as BigQuery. There are others that are very popular as well, such as PrestoDB, an open source project that you can actually run on premises. There are others. These serverless data warehouse technologies allow you to gather these massive amounts of semi-structured data, typically JSON formats, but also other formats are possible, like more of a legacy format known as XML, extended markup language. So it's possible to collect a lot of this data in the original semi-structured format without forcing a conversion from semi-structured into a structured format. So this means that as a developer, you don't really have to take those nested arrays and unpack them into rows or unpack them into different tables. You don't have to unpack dictionaries inside of these semi-structured formats into separate tables. You can basically store the data as is. Think about storing JSON data almost as is within these serverless data warehouses. And really what the talk was about is what happens after you have built up a data warehouse of the semi-structured data sets. How can you efficiently query this data, and how can you efficiently use that data to generate insights? So I think this is still a young topic. This field is still maturing. Obviously, not as much work is happening with semi-structured data as with unstructured data or structured data. So I think there's still a lot of opportunities for growth in this space.
Awesome. Yeah, and I surely included the link to the talk on the show notes. People can have a chance to listen to it and kind of see in total how your explanation of semi-structured data really matters. Since March of 2019, you have been acting as the Chief Technology Officer of Counterfactual.ai. So can you talk about the company and your work there?
Absolutely. One of the reasons why I decided to shift gears and work at a small company rather than Google is that when I joined Google, it was actually smaller than IBM. But at the time when I departed Google, it was already over 100,000 people. So it grew very rapidly during my tenure there. And at Counterfactual.ai, I really have an opportunity to have full responsibility for all the technical strategy, all the technical decisions that happened within the company. And this is something that I wanted to focus on for a while. So if you're interested about the types of work that we do, I mentioned earlier that we do a lot of work with PyTorch and with Amazon Web Services. That's what my customers are asking for. Just to give an example, this is a use case that we started working on prior to COVID-19, but actually during COVID-19, it became surprisingly relevant. So one of my customers is responsible for a highly local food delivery. So one of the models that we worked on was to improve estimated time of arrival predictions for food delivery in very specialized areas in niches, and also do it in a way that does not rely on external APIs. So imagine doing travel between two different locations within an urban area, and instead of using cloud-based APIs like Google Maps or Bing Maps APIs to estimate the routes, you would use locations, like think latitude and longitude locations to estimate the delivery time between these two pick-up and drop-off points. So this is an example of one of the projects that I've been working on. And in fact, serverless machine learning, the book is inspired by this use case. So in the book, I also talk about approaching this kind of a problem and walk the reader all the way through the business use case, all the way down to deploying a system into production. Mm-hmm. So if you're really interested about the kind of projects that I'm working on at Counterfactual, check out the book.
Yeah, and talking about serverless machine learning, so you led a workshop on serverless ML with TensorFlow at the Reinforced AI conference in Budapest last year. So the workshop introduced the process of building a complete machine learning pipeline from data ingestion, data exploration, model training, model evaluation, model inference, and model deployment. So can you quickly, walk through what you cover in that workshop?
Absolutely. So that workshop was before I actually started using AWS and PyTorch for my customers. That talk was still based on TensorFlow. But at a very high level, the talk was about teaching primarily TensorFlow to the audience. So the talk started with an explanation of how to build simple machine learning models in TensorFlow. For example, building a linear regression model, and then using TensorFlow capabilities to scale that model up. So the talk focused on using the TensorFlow Estimator API. So that was last year, it was TensorFlow 1.0 days, or 1.x days rather. I think we used TensorFlow 1.15 at the workshop. So we used the legacy TensorFlow Estimator API to help build out those models. And with those Estimator APIs, we talked about how to deploy the model into Google Cloud. So how would you actually take the model and connect that model to the data stored in Google Cloud Storage, and also how to take that model and make sure that the models can run on what is now known as the Google AI platform. So very much a TensorFlow-oriented talk.
Right now, at the moment, you're writing a book with Manning called Serverless Machine Learning in Action. So it is a guide to bring experimental machine learning code to production using serverless capabilities from major cloud providers. We already talked about the book throughout the conversations thus far, but what else can you share with the listener about the book at this point?
You have a very diverse audience of listeners. So the first thing that I think I'd like to do is to explain the purpose of the book. So I wrote this book for practitioners who are interested in becoming more productive contributors to their projects, teams, organizations. So the book will not make you a better machine learning researcher. It will not teach you machine learning algorithms, or it will not teach you the theory behind machine learning. That's not the point of the book. The book is about helping you take what you already know about machine learning. So the book has fairly low level of entry, low level barrier for machine learning practitioners. If you've done linear regression, if you've done logistic regression, if you have some basic understanding of taking data sets and partitioning it into training, validation, and test data sets, I think that's enough for you to get started with the book. But what you can get out of the book is a recipe or collection of tutorials that will make you more effective at taking your machine learning ideas and actually putting them into production in a way that helps you avoid what I call the machine learning operations trap. So machine learning operations, ML ops trap for short. This is when you, as a data science or machine learning practitioner, build a model, put that model into production, and then find yourself having to spend more time on keeping that model up and running in production, meaning tending to things like availability, keeping track of latency for that model, keeping track of the number of requests, as opposed to doing what you do best, which is creating better models and working with data sets. So this ML ops trap is something that I've seen happen with multiple customers, where the company takes highly compensated machine learning data science practitioners, and instead of having them work on data science problem, they work on these machine learning operations, ML ops. I think that's a mistake, and I think the best way of addressing this ML ops problem is with serverless, minimizing the amount of effort that it takes to do operations, automating that operations concern with the public cloud providers like AWS, Google Cloud, Azure, and really freeing yourself up to work on machine learning.
And also, from reading the table of content, you actually also already mentioned it, but the book will show how to implement models with PyTorch and use PyTorch lining for distributed ML training. So, can you talk about, this sort of choice of frameworks to go with PyTorch, just in broad?
Absolutely. I think as early as the beginning of last year, so for the listeners, the beginning of last year would be the beginning of 2019, there was concern in the industry that PyTorch is not quite mature to be a production machine learning framework. And I think if we look at the situation today, which is mid-2020, PyTorch has clearly proven itself in production. And when I say proven itself in production, I mean PyTorch today scales from obviously mission critical use cases at Tesla, right, with the Tesla self-driving vehicles, to cutting edge research with organizations like OpenAI using PyTorch and standardizing on PyTorch. So I think if you have any concerns about whether or not PyTorch is a production ready framework, I think that you should put those concerns aside. The reason why I decided to settle on PyTorch specifically is the philosophy in the PyTorch design. As an engineer, I like to work with the technologies that provide two pathways for using the technology. One pathway is where I can drill deep behind the components, really drill deep into how the technology works. So for example, if I wanted to go in and really understand and tweak the PyTorch AutoGrad, the automated differentiation feature, I can do that. And at the same time, the technology provides a collection of abstractions on top of these low-level capabilities. So as an engineer, I want to be able to have a very well-documented APIs, very well-documented set of components that both work at a low level and a high level. And my really favorite example of that is the C programming language. So with C, if you want to, you can drill all the way down to the assembly language and work at a level that's as close to the metal as you can get. But at the same time, you can start building out your own structures. You can build out your own pointers. So without losing that connection to the fundamentals. And PyTorch gives me a very similar kind of an experience. And you mentioned PyTorch Lightning. I think PyTorch Lightning is valuable for this very same reason. It automates or standardizes on common usage patterns for PyTorch without trying to hide what's going on behind the scenes. And I think actually that's one of the reasons why the NeurIPS conference standardized on PyTorch Lightning as the framework for paper submissions.
There's a lot of different libraries currently being built on PyTorch, and definitely PyTorch Lightning is one of those open source framework that is sort of ahead of the rest. I think. I honestly have been paying a lot of attention to that community. So hopefully I can get more intimate with it and understand more of the different use cases of PyTorch Lightning in machine learning in general. The book will also use AWS to host and run the serverless machine learning pipeline. So in your opinion, what are some of the pros and cons of using AWS compared to other big platform players such as Microsoft Azure or Google Cloud Platform?
I think if you take a look at the platforms like AWS, GCP, Azure, there's a fair amount of commoditization that has happened. So there are some capabilities across all these platforms that are nearly identical from a standpoint of a machine learning practitioner. So in fact, in the book, I talk about using features like object storage, serverless object storage from these providers without really caring about the details of each individual provider's capabilities. If you have object storage from AWS, you're going to be able to pick up object storage from GCP without any problems. So I think given that basic level of commoditization that has happened, some providers have strengths in certain areas. For example, I find that with GCP, there's clearly strengths in the areas like AutoML. But I think the other vendors are investing so heavily that the distinctions, as soon as they become obvious, they get eliminated very quickly. So today, if you are interested in picking out a cloud provider, you should be focusing more on non-technical issues and ask yourself about what does it mean for your customer to pick a cloud-based provider? Does it make sense to get locked into a single cloud vendor, or does it make sense to try to build out more of a multi-cloud solution where you can easily migrate across different clouds? So I think the reality today is that if you pick up technologies like serverless, if you pick up technologies like Docker, if you use PyTorch, for example, you can build solutions that help you migrate across these different clouds, if not with a click of a button, then I would say fairly easily. And as a consumer of these clouds, you can avoid lock-in. or avoid lock-in as much as you can, and have that flexibility of switching cloud providers in the future. Because I think today, betting on a single cloud provider is not going to give you a differentiated advantage in the marketplace.
Yeah, thanks for sharing that opinion. So lastly, I understand that you are based in Orlando, Florida. So you're just very curious, how would you describe sort of the data and tech community down in Orlando?
Oh, great question. Obviously, when you think about data science, machine learning communities, and cities, Orlando probably doesn't come up as front of your mind. Clearly, the community is not as well known as the community in the Bay Area, Seattle, Boston, New York. So Orlando is definitely in the middle of the tier, but there's something that makes the Orlando community stand out. And this is actually one of the reasons why I'm working closely with the community here. And it has to do with the focus on the simulation industry. So I mentioned a little bit earlier when we talked about the research paper that I did on multi-agent systems, is that simulation-based studies are very important. And I think the machine learning 3.0, if I were to describe it that way. So if you think about machine learning pre-neural networks, I would say that's machine learning 1.0. Machine learning with deep learning, I would call that machine learning 2.0. I think machine learning 3.0 is going to rely very heavily on simulated environments. So think about using almost like a virtual reality style engine and using those virtual reality type environments to train machine learning models. And I think we're seeing more and more examples of that in production. What makes the Orlando, Florida community stand out is its historical experience with simulation, the skill set that exists in Florida around building out virtual reality environments, building out gaming environments. Universities like Full Sail University that produce artists experienced in 3D rendering, experienced in building out virtual worlds, and experts in using different game engines from the programming standpoint. So I think Orlando, Florida is not top of your mind for machine learning 2.0, but it's very well positioned to race ahead for machine learning 3.0.
Yeah, thanks for sharing that. Very interesting story and how the community down in Florida is different. Yeah, it's always great to hear how people get into machining from different location areas. So yeah, it's awesome that that you can tap into existing resources of a community to leverage the work that you already doing. Carl, at this point of our conversation, I want to move on into the final closing segment, in which I'm going to ask you 3 rapid fire questions, and then you can give tactical answers for the listeners. The first question is that name 3 people in the cloud computing and machine learning universe whose work you really admire.
Okay, so I think I'm going to focus on 2 individuals who are more on the machine learning side, and I'll call out 1 individual on the cloud computing space. So the first individual that I'll call out in machine learning is Jürgen Schmidhuber, and he is not as well known as he should be, particularly based on his work on LSTM machine learning models. And I think he is an underdog in the machine learning community. So while other machine learning researchers have gained more prominence, I think what I admire about Jürgen is originality of thought and his willingness to persist in working on machine learning, his willingness to concentrate on the space despite the fact that many other people are getting credit while he's not getting the recognition that I think he deserves. So he's the first person that I admire. The second person that I admire, I would say, Salman Hikes. So he is more on the cloud computing side. And Salman is really the driving force, effectively the creator of the Docker technology. So right now, Salman Hikes is the CTO of Docker, the company. What I admire about him is that he took extremely complex technologies, so Linux, C groups, namespaces. So fundamentally, these are complex technologies, but he transformed them into easy to use toolkit. Mm-hmm. So I think this ability for an engineer to make complex easy to use is something that I really admire. And I think as a technologist, he did a transformative thing to the industry with his Docker project. I don't think he's getting the recognition that he deserves. And then finally, the last individual is Dana Bellard. So I mentioned Dana Bellard as one of my professors when I was doing undergraduate research projects at the University of Rochester. So today, Dana actually moved from University of Rochester to University of Texas, Austin. But he was really influential on me in the areas of machine learning. And what I admire about him is probably his approach in the book that he wrote, Natural Computation, where he effectively laid out key topics for machine learning practitioners that are still relevant today. So I think his book, it concludes with game theory as an example for machine learning systems. So I think as machine learning practitioners, we still need to come to grips with the influence of game theory on the design of machine learning systems. And I think there's still a lot that can be harvested from those initial ideas that he helped plant in my mind and in minds of his other students.
And the second question is, besides the book that you're currently writing, can you name one book that you would recommend for people to develop a data engineering mindset?
The Gang of Four book, Design Patterns, I think it's one of these that's an oldie but goodie. So the book is actually about C++ based implementations of design patterns. And this might put off some people, but if you are an engineer, I think we need more engineers that are comfortable with this style of thinking, where you take something very complex, like the recurring pattern that exists in C++ code, and then codify that into a pattern. So essentially identify this valuable pattern of usage of complex systems, so that later you as an engineer, or maybe other engineers, can take these patterns and build higher order, higher level systems out of them, more abstract systems, more easier to use systems. So if you want to become a better engineer, I would say take the Gang of Four Design Patterns book to heart. You can learn a lot from it.
Finally, imagine that you send out a tweet to all the aspiring machine learning practitioners on Twitter. What could you tweet about?
I would say find yourself a data science mentor, and if you can mentor others in data science, do that. And in fact, putting that tweet aside, I would say if somebody is interested in having me as a data science mentor, reach out to me on LinkedIn. My contact information is on my blog, cloudswithcarl.com. So I think I've been fortunate to have great mentors in my career, and I think I need to give back and mentor others.
Right, awesome, Carl. I think that's a very positive way to end the conversation. And I really enjoy sort of hearing about your background, a little bit your early exposure to machine learning back in the early 2000s, your whole career from contributor as a software engineer at IBM, and then later on leading various production-ready systems at the company, your work democratizing machine learning at Google, speaking at various conferences and events, sort of the discussion on, serverless machine learning overall, some of your client projects at Counterfactual.ai, as well as your book currently, being written and hopefully being published soon. And I be sure to, included all the links, resources into the show notes, so listeners can have a chance to dive deeper into the materials that we discussed in our conversation today. And I'll reach out to you if needed. And so, Carl, really appreciate you spending your weekend speaking with me today, and I hope you have a great rest of your day.
Thank you so much, James. This was a lot of fun participating on your podcast. I really liked your questions and really enjoyed speaking to you. Have a great weekend.
Well, that's the wrap for another episode of Datacast. Hopefully, you have learned something insightful and interesting from my guest today. You can read the show notes from the podcast website at datacast.simplecast.fm. If you want to get instant updates when a new episode is released, either follow me on Twitter or subscribe to my newsletter on my website jamescayley.com. It is my greatest pleasure that you listen to this podcast and take advantage of the data revolution coming upon us. Goodbye for now.